Okay, yeah, thank you. So I said the first thing is we have discussed some part of the mathematics, physics, and possibly the approaches that we use in the theoretical settings that forms the background for quantum computation. So now I want to delve more into the tools or the fundamentals which form the tools that are employed for quantum computation. So I discuss the abstract and then go straight to what the base of quantum computations are like. Then I give some references and I go. So I have a shorter time and I'll try to manage my time as fast as I can. So I said in this talk, I shall state the basic fundamentals which are required for quantum computations. And first is to look at some terms which are generally used. Now, quantum communication. What is quantum communication? Quantum communication is the act of transferring a quantum state from one place to another. And this is generally used in classical computations. But what we use is to say that we have an Alice and a board that want to pass information from themselves or to themselves. Okay? Now, the basic motivation is that the quantum state, which is a code of a quantum information called the qubits. Okay, in the case of a two-dimensional Hilbert space, because Hilbert space, because Hilbert space takes the real and complex variables, so I mean it's the best space to use, and that the quantum information allows one to perform the task that could only be achieved far less efficiently, if at all, by using classical information. What I mean is, like the last question that was asked, where I gave an example of what the speed or how fast or how simplified the quantum information will travel or how elaborate it could move information is exactly what is being described here. Now, next is that what are the quantum computers? Quantum computer is a device that processes information in a quantum mechanically coherent fashion. Okay, the principle it exploits the coherent quantum interference and entanglement to perform computations such as factoring large numbers or searching an unsorted database. Now, this is done much faster or rapidly than what the classical computers will do. Okay, there are a number of shortcomings, difficulties, but then it is also shown that with the algorithms of quantum computation, I mean, you can achieve more in very fast and easier positions or ways than it is done in classical computer. So, examples of where this is used is in the manufacturing problems, optical cavities, and some other application areas. Particular optics is a core area where quantum applications fall into. Okay. Now I said optical cavities offer promising experimental approaches, but no quantum algorithm has yet been implemented with those systems. Then when I wrote this, computer knowledge has shown that there are a number of work that have been done. And people are still working on that. That's where we are on. For example, nuclear spins are particularly good quantum bits that can be used. And this, I guess, we can also read further on. Then, what is the basis of a quantum computation? For a quantum computation, we talk about quantum bits. For classical bits, we use zeros and ones. For quantum bits, we use matrices and then a combination of zeros, 0 gates, and 1 gates, and 0 and 1 gates. Okay. Now, these zeros and ones are either in the graph form or in the position form. That's exactly what these are. And if I use a 0 gate, it's a row matrix, which is 0, 1. If I use the 1 gate, it's 1, 0. So you can visualize this generally as a north and south poles of a sphere of radius 1 called the block sphere. For the block sphere, you can estimate the angle of rotation and things like that. That is when you have to do more clear computational things. Now, in classical bit, the states are either zeros or one. And in the quantum state, the loss of quantum mechanics allows the state of a qubit to be a combination of 0 kth and 1 kth, called the superposition. And the state in that case, an example is to have it represented like this, where you can use both states at the same time. That is where it is easier for you to determine how fast or the speed by which a quantum computation can be done. Then you also have the plus state, the minus state, and the plus I state, and the I state. This is what it means. I think the last slide was the minus I, not just I. So you have the plus state to be this representation, the minus state to be this representation, the I state. You can see that the plus and the I only have an I added. Okay? And the same for the minus I. You have a change in sign. Now, these are standards that are known. I mean, you can read them up in many books on quantum computation. So a quantum state is normalized. Okay, if its probability is 1. For example, you can have this as a normalized state by finding the marginal constant A, such that it ensures that the total probability is 1. Now, when some of these terms would come up many times, okay, and they also are used in quantum physics, but I brought them in here so that we can get to familiarize ourselves with it. Okay, for example, I have, okay, let me read. I said physically, any quantum system with 2 distinct states can be used as a qubit. While one is expected to be familiar with quantum physics, some examples are 1 photons. In physics, there are so many of those, I call it micro, or how do I use those more particular particles? You have photons, you have phonons, you have xenons, subatomic particles. Yeah. So, I mean, so here, a photon or a quantum particle of light have a particle polarization. Now, a photon polarization can be vertical or horizontal, or you have a superposition of both, and we can use this as a qubit. So these terms come in to help us see what the representation, the superposition principle, I mean, this, which is more general, looks like, or this. Okay? Therefore, another example is the trapped ion. An ion is an atom that has an overall charge instead of being neutral. Okay, because it has gained or lost 1 or more electrons, individual ions can be trapped in space using electrical fields. 2 energy levels of an ion can be used as a qubit. Okay, these are examples of qubit. Then you have the cold atoms. Well, you know, I told you that I had to a lot of effort to do some physics, and when I was trying to learn, these terms come up so many times in quantum optics. So I needed to really see it, not even doing the computation, but even in the theory. And that's exactly why I brought them, because I also had to familiarize myself with this. I know that in quantum optics, there are a number of theories that are already existing, but they are lab works. Okay, so the computations, we are now trying to work on them. Okay, so you get to familiarize yourself. So neutral atoms, that's what cold atoms, can be trapped at low temperatures using a magneto-optical trap, which uses magnetic fields and lasers to cool and trap the ions. So another approach is using an optical lattice or lattice constructed by laser beams. Once trapped, 2 energy level of an atom can be used as a qubit. So most of these have some theoretical background in physics, and I mean, you want to get to see it more, please, you have to do more physics to be able to do. But they are just examples of qubits that we are trying to understand or see the way with computational tools where you can use them. So you also have the nuclear magnetic resonance. The nuclei of atoms and molecules have a quantum property called spin, which can be used as a qubit spin. As a qubit, spins can be identified by their frequency of pulsation when subjected to a strong magnetic field. So you have spin up, spin down, and it's represented as a column matrix. Okay, you have quantum dots. An electron can be found to be a small semiconductor device similar to an electron bound to the nucleus of an atom. In these artificial atoms, the spin of an electron, which can be spin up or spin down, can be used as a qubit. Then you have different qubits, a diamond crystal which have a missing carbon atom, and if you replace the carbon next to this frequency with a nitrogen atom, you get a spin triplet. That can be used for quantum computing. This is called a nitrogen frequency center in diamond. Then you have superconductors. I think IBM uses superconductors. Yeah, so in a superconducting circuit, charge flows with zero resistance. The magnetic flux across an inductor and the charge on the capacitor causes a harmonic potential energy with equally spaced discrete energy levels. Now, quantum gates. In the classical computing, our gates are zeros and one. And I have another slide which I would have loved to use, but unfortunately I can't find it. In that slide, I connected what we do in logic. You know, in logic, if you have statements, unfortunately my board cannot be cleaned now. You have a table, we call it a truth table. I mean, if you have done further maths in those days, or you have done logic in university, you have a truth table where you can combine. If you have, I mean, a truth table for true and false, and then in that case, it will be maybe a P, okay, which is used as, if you have two cases, you have 1, 1, 0, 0, and you have 1, 0, 1, 0, and you have a Q, okay? Like I mentioned there, in classical case, the maximum occurrence can be for two statements. You can have 4 possibilities, so you can have the 4 possibilities this way. Then, what we used to do in that case is to check our this or this, and use this and this, okay? Then we can find their negation, negative P, I mean, then not just minus, but negative P. Then you can combine the combination of this. Okay, so in that case, we used to form a table, a truth table like this, and we have P, or I mean, 1 on 1 would be 1, 1, 1, 0, and for and you have 1, 0, 0, 0. I think that works. Okay, I don't know if there could be errors, but I mean, just try to correct me. Negation would be 0, 0, 1, 1, and the negation of Q would be 0, 1, 0, 1. I mean, so in this case, this kind of possibility is to determine how the information you process in a computer works with this. All the information you put into the computer system goes back to 0 and 1 and follows this truth table. And then you call them gates. Okay. The same way we have gates in the quantum realm. And such gates are the ones mentioned earlier that are examples. Here, our quantum gates act on qubits. And like the logic gate is the one I mean by the classical cases, okay, they act on bits. A quantum gate transforms the state of a qubit into another state. Generally, we use U. So U is used to denote the quantum gate. So our quantum gates, there are very many types, okay? We'll soon see them. But let's just consider a quantum gate that performs the following map. Well, in mathematics, the term map comes very often. Okay, why map? Because it is a transformation. Okay, you have an F, taking a value from a domain and taking it to its range. So in that case, you put an element here and it takes it there, and you have a transformation F of X. This is a picture that you can create with mathematics. But here, our action U is on the ket. And on ket 0, you can have this possibility. I mean, this is just one example. okay, of how the gate is. So you on get 0 call it this, and you on get 1 call it this. Generally I tell some students, if in mathematics we tell you this way we define this, we are saying that see it like this and follow what we are saying. So our gate is defined this way. Now, every gate must be linear. I've talked about linearity. You remember I mentioned that to you. Okay? And then we try to look at it. What does it mean? In linearity leads us to what we call superposition. If you students will understand what superposition is better than even me. But me, I shall know that, okay, we're talking about linearity. That's not it. Therefore, if I want to see what this gate will do, then I know normalization would mean making the gate become 1 at the end of the day. Therefore, if I combine the two, for me as a mathematician, because I try to come from a mathematics perspective, I am looking at that kind of function, whereby I can show linearity. Therefore, you can see just the way my f, what I mean is, my f goes in, it becomes alpha f of x, and my f goes in, it becomes beta f of y. Now, if you observe, if this is my f, and I have alpha x, our x is a bit, our y is the other, qubit, and then my alpha and beta remains. So I want to try to express what I have. So this is the idea from the perspective of mathematician will hold it. So our gate comes in, our alpha and composition that beta. Then I try to what to do in math to connect like terms. Get zeros, get 1. And that simplifies to what I have here. You can see my K0 is out. I bring this here, then factorize, and I have alpha, beta. Okay. Now I said for this to be valid, the valid quantum gate, total probability must be what? Must be 1. So these are the ideas you must stick to, because you have a normalization that must always occur in this case of quantum gate. So assuming the original state was normalized to be alpha absolute value squared plus beta, this is standard in physics. Okay, our coefficient must have this representation. So we can calculate the total probability by assuming the norm. We talked about norm before, and I told you what norm is. Okay, a norm is a positive number. Now, if you have complex numbers, the only way you can make complex number positive is to take the absolute value and square it. And that is the idea here. Already you can see a complex value here. So you can see the complex value here. So normalizing will mean take the absolute value and square. And then the norm square in that case, physics call it amplitude. So let's see if you simplify this, does it lead us to that value giving us 1? And that is basically what was done. Now you observe here, because of this complex value, you remember that when we were talking of Hilbert space the other time, we talked about integral something like phi star phi like this, and well, maybe the whatever it is because of the integral. But what I really need here is these two values are conjugates. Then you need the absolute value, and that's exactly what is happening here. This absolute value would now become absolute value of phi. Okay, because by the time you get what is here, this will give us a real number. Now, if you look at what I have here, being complex and taking the absolute value, also being complex, taking the absolute value, you come back here to show that the first one is like what I wrote before. Okay, I have the complex number and its conjugate. I mentioned this when I was talking about star operation. Okay, that if I take a star operation, the way it works, okay, having an evolution of this changes the sign, okay, and then you have your constant, they are changing to the alpha star. That evolution acts on it, okay, and the other case also happens the same way. But in a simple way, it looks like what I gave before when I was talking about phi x to be a plus ib, then phi star will be a minus ib. I mean, so that operation will now becomes that representation. When you now simplify it, you can work it on your own. It simplifies to giving us back, break it down, expand, simplify, you get absolute value of alpha squared plus beta squared, which is what we are asking you to check, and that gives you 1. Okay, that guarantees it to be a quantum bit, like what we wanted to do, to show that this is a quantum gate. That's the question, and that's what we have expressed, and we're able to see that. So I said here, the conclusion that U is a valid quantum gate. Then quantum gates are linear and they keep the total probability equal to 1. That is a standard thing. So because something a quantum gate will satisfy this condition. So some other examples of quantum gates include the Porty gate, Qiskit, the Adama gate, the control knot gate, the block sphere. And that's why I'm not really too happy that I have to get here first, because in the classical gate, you have all these gates also active. You have general, you have some of you have done circuits in physics. You have something like this. I think this, I can't remember whether you have the notation there. I don't want to make mistakes. Okay, I mean, I know you have a diagram that looks like this. Then you have a diagram which shows some kind of negation. Okay, and in that case, all those ones work for classical gates. But here you have the same principle, and that's where each of these gates come to play. Then I think for our U, our quantum gate U generally comes to be either ket 0 or ket 1. And if it acts U on ket 0 gives us this kind of, I mean, A and B are the states, and you can see that it gives us an AB, while I mean, if you get U acting on ket 1, I mean, represents just any algebra or any value, okay, CD, and you have it that way. Then rearranging it side by side, if I had AB to be 0, 1 and D or CD to be 1, 0, I mean, then you can see that my U will become a matrix. What I mean is this: if my AB is 0, 1, 1, 0, I will have something like 0, 1, 1, 0, and then it will be a matrix represented 0, 1, 1, 0. I mean, and this is the kind of thing that our quantum gates will represent. So if I now take it, act it on ket 0, our ket 0 is generally, I mean, represented this way, and our ket 1 is represented this way. So if my gate, by mere multiplication, act on this, it gives me this. It takes it back, and also this, it gives me this. So this is what our quantum gate looks like. And when you act that on it, then you have any ket state to be represented as alpha ket 0 plus beta ket 1 as alpha beta. That's what that one has shown us. So I'm still going to give this slide. Maybe after the class, you can send it to everybody who have email, so you have it there. You can look at it thoroughly and check some of the things that have been done. Then I also give some references. In those references, you can read more on the basis, and that basis will form your strength. I mean, you can't do but read. In maths, and you can't avoid that. So then, applying U, given any state phi, our ket state, if you apply U on it, okay, is an action. That action gives us the superposition of that, and we have it as alpha of the whole of this, beta of the whole of this. Now, if you simplify, you get a matrix written as this one. Then your matrix can be written to can see the U acting on that ket phi as A, B, C, D acting on alpha beta. And that gives us the matrix, a column matrix. So it becomes a standard that you can use. So whichever values comes in, 0, 1, I, 0, 0, I, or minus I, depending, then you can use this to simplify. So hence, in the language of linear algebra, quantum gates are matrices. I'm sorry for this, you can correct it. The matrix must ensure that the total probability remains 1, which is what we try to also expand or show here. Those multiplications can be done. Therefore, we state here that the quantum gates are matrices that keep the total probability equal to 1. And for example, if you pick this, the gate U acting on ket 0 with the complex linear expression that you have, okay, just like you did for using alphabet, which is a more general term, but now you have 3 particular complex value functions. And then, if you add your U on it, it gives you this transformation. You add your U on Y, on ket 1, it gives you this transformation. Then our gate becomes a representation of this form. I mean, and you see, when you have this, you can also write it in some ways. You can factorize half out, do so many things, and manipulate it. It depends on how you want your expression to look like. But this is just guaranteeing how you can work or simplify with quantum gates. Then you let the identity gate for the X and Y. I didn't mention the X and Y gates before, but I mean, they also exist. Okay. So you have the X gate, the Y gate, and I think I have a list. I don't know if I have it on this laptop that shows almost all the gates you can use in the, but you have X, Y, Z, then you have the Adamant gates. And that representation all gives matrices. So of particular note is the 2 by 2 matrix, which is given as 1, 0, 0, 1 as an identity matrix. This we are very familiar with. When this acts on any vector, it leaves it unchanged. Our identity matrix is just a mirror. You look at the mirror, you see yourself. So the reflection gives you the same, and that's exactly what has happened here. If you take your identity matrix as your gate, it gives you back what you are starting with. Okay? And you recall that if you transform ket 0 and ket 1, it gives us exactly what we are starting with. Ket 0 acts on A and B to give AB. Ket 1, the user acts on ket 1 to give us C and D, just like so. That gives us an idea of what we see in what the identity matrix is. Then you can be written as a 2 by 2 matrix in this form. This I think you are very familiar with, particularly those in physics. But I mean, with time, some of these things stays with you. So given the state ket phi as alpha ket 0 plus beta ket 1, if you apply a U on it, it gives you what, for me, I call it a linear combination. But you can see that you just multiply this matrix with this, and this is a column matrix. So U acting on ket phi is a column vector. Hence, if you take the U in, it gives you exactly U out to the ket phi. It doesn't really make any, I mean, just like what you call linearity, okay, in the components. Now, consider the conjugate of the transpose of ket of U phi. Okay, that gives us what we have. Okay, like the question he was asking before, the action of the star operation and how it connects with the adjoint operator. Okay, all this as simple math by, if you take our U to act on ket phi, we have these two expressions. By rearrangement of multiplication of matrices. Okay, just like we have our row and column vector of ket multiplying themselves, giving us matrices. This is exactly what happened there. But now you reverse it by factorization. Okay, and this gives us what we have. But you can see the operation of star actually gives adjoint. That was the last question the other man asked me. Okay, and I showed the connection, and that's why you will see. Sorry, this should have been in bracket this way. You will see that our U of get phi is this as get phi acting on U of the adjoints. Okay, and just the same way that I described the evolution in mathematical concept or mathematical terms, the adjoint behaves like that. So you call the adjoint of a ket phi as a bra. And that is exactly what was shown here. So you can look at that and see step by step. These are some of the things that in the algebra of some concepts in operator algebra, this also are shown. Summarily, I said U phi ket is seen as, U acting on ket phi, and if you take the adjoint, it's seen as bra acting on U adjoint. So using this, we can consider an easy way to determine whether a matrix keeps the total probabilities equal to 1. So you consider a quantum gate, which is a matrix U. If it acts on the ket phi, we have this to hold. It becomes a standard result. And because it's done in abstraction, obviously, it always remain like that, because our A, B, C, D can be just any value. And so if you go for the abstraction, then if you have numbers, you can also determine that. That's what this is talking about. And the same way, for you to be a quantum gate, the normalization must hold. And that is the inner product of the ket of U phi is itself to be equal to 1. And this becomes a standard. You can see that in our analysis in math. The standard thing that if this holds, then you say it is unitary. That's what we call it. I guess it's really the same thing. Yeah, so if an operator obeys this rule, then it is unitary. So a matrix that satisfies this is called a unitary matrix. Yeah. Okay. If you take a matrix, multiply with the adjoint, and it gives you identity, okay. In matrices, particularly, we call it invertible. That's our inverse. Okay. But this generally is for all operators. So if this holds, then you say it is unitary. Thus, quantum gates are unitary matrices. And unitary matrices are quantum gates. So as an example of application, we pick a particular one, then you see that this unitary matrix is complex. So you don't expect it to behave like when it is a number. And these are the beautiful things that this presents. Now, what is your U? 1/2 with the matrix 1i minus i1. Then what is the adjoint? Take the multiplication. What does it give us? Does it give us I? Okay. That's the kind of thing that is being done here. And you have U, dagger, U. You have the two matrices, multiply it, gives us 1i minus I and 1. And in that wise, you can simplify that and get whatever that looks at. But basically, I have just brought this just to show the simple operations that comes with gates. And generally, all the gates, you can work with them to simplify it in that way. Now, I promised I was going to mention some references. And these references will be very essential, okay, for you to be able to work more. This is a book. This is a book. This book was 2022. When I did this work, this is a older book. There is nobody that does anything about computation that will not refer to this book. Yes, it's the most standard book, and it's always the beginning book for everyone. There is a more recent book from IBM, which I just printed. I think Mr. Victor, Mr. Victor sent the book. This is Quantum Information and Quantum Computation by John Watt. It's a 2025 book. It's also a very essential book. All these books, I mean, there is no one that you pick that will not give you the exposure required. But the best is to always work with more recent books. Yeah, because you have updated knowledge. There is active research. And let me advise, you are all young. Okay, if you want to do active research that has funding, the field of quantum computation remains a very good area to go to. I remember somebody that didn't allow my passion to die. It was a lady that came here from the US last year, and I mean, we hosted her. She was telling me when we were discussing on something, and she was like, this quantum area that you are working in is still one of the oldest areas that you can get funding. And some of the things I keep doing is to ensure that, okay, I'm alive in the system. Part of being alive is to ensure that I'm able to also bring out the best in some of my students, then push them also to work in these fields. They might not know the value, but when the opportunity comes, so these are areas that you can look at whatever you want to do that relates to it. I don't think there's anything that is odd in it. So that might be some of these are some of the books from mathematics. Okay, the first one was a book written by a professor of physics here in UI, while the second one is a standard book that uses Hilbert spaces to explain concepts from quantum physics and mathematics. Yeah, I like the book because it makes me see the mathematics of quantum physics. Okay, so these are references that you can look at when I send the material to you. I think after this, you can send this particular material to everyone. Yeah, so that is where I'm going to stop. I hope I've made up the time or less of the time that you gave me. So for the day, I have justified the classes I exposed you to. No matter how rigorous it looks now, it is still simple and straightforward we have given it. So if you handle the materials that I have mentioned, you get access to the tools I have used then to start learning. So from further lectures, most of these terms will be used and talked about. Now you are familiar with it, it will be straight. By the end of the day, if you have brought your laptop, some of this, the Qiskit will be installed for you. So starting from next week, we'll be doing hands-on. You work with Python. Okay, look at this code, write it this way. You see the way it runs. You build circuits. And from building circuits, we are already talking about the computer. And so you enjoy it more. Or if you don't have a laptop, it's punishment. You have to pay for one. And so yes, because I told them in the computer class that I was teaching in my department that look, if you are learning any competition and you don't have a laptop to use, you are just learning in vain. I had so crazy experiences with that. So many times. In fact, my last laptop, everybody can see that is a very bad one. I have two good laptops, okay? God has molded me. So I think it's also something I have to encourage you to process. So that the spirit of working with this does not die. Then I think if an IBM speaker is going to give us talks, he will also tell us where the opportunities are and what areas we can dive into. The only beautiful thing I've seen is that no matter how much of physics you talk about in quantum computations, the mathematics is central. Yes, it is central. You say quantum optimization. I mean, how will we do that without mathematics? I mean, in coding, you say quantum coding. What do you want to code without mathematics? I mean, so these are almost all the things that makes it good for us to work together, collaborate, and build ourselves. So I would love it that everyone that is here now is able to continue in the field. Then subsequent times and years, we are also able to work and collaborate together. So thank you very much. This is where I'm going to stop. Yes, ma'am.
Do we have any discussion for Dr.
Oh, last Sunday, Sundays or not?
What about online? To think of your question now, you can ask question. Okay. We have no question. Okay, I think we can take a moment break, then we'll start with the answer session. So whilst we are having the answer session, we should have something to do.
I'm so sorry. I had to quickly pick that up because I didn't put. So yes.
So I'm going to do, there's no question.
Okay. Thank you so much.
So let's give a round of applause. Please take like 5 minutes break so that we can set up an answering session. So whilst we are doing that, we'll have our meeting.
Okay. For those who have their computers,
yes. For those who
let us start what we are going to do. This is the trend, though. This is where you have to go to. You want to do so one year. Oh, I hope Victor is online. Yeah.
Hello, everyone. I don't know if I'm audible. And yeah. Can someone confirm that you can hear me from the camera?
There's no response.
Hello. Okay.
Can hear me? Okay, fine.
Yeah, I think the video is off. I would like to see what the screen is showing. Okay. Can you see my screen? So is my screen visible, please? Just I need someone to.
It's speaking. This camera, so you will speak. Hello?
Yeah, I can hear you. Do you need me to speak? Is it
No,
better?
we are texting whether the mic is working.
Okay. So how is it now? Is it doing fine?
I think it's fine.
Okay.
This is the mic.
So you confirm that I can start now?
Yes, sir.
Okay. Good afternoon, everyone.
John, welcome to Qiskit
QFF for University of Ibadan Quantum Computing.
So nice that we are holding this event this year. And more than we
Did last year. I think that this year we have more days for us to learn the basics of
quantum computing program, particularly using IBM.
Qiskit software. Yeah. So firstly, I would like to say that Qiskit is from IBM, and when you say
Qiskit focus. So Qiskit. So it's from IBM. Basically, for those who are well versed in programming, they have what they call the SDK, that's the software development kit. And for IBM, they have developed a software for quantum information. So for quantum computing and information programming, and that is what we call Qiskit. So what I'll be doing for us today is to, first of all, take us through
what you are going to be doing in few days, and then also to show you
what level of that is. Can you hear me clearly?
Okay, fine.
All right. So please, if there's any question, you can just pause and ask me again. So I know what you are seeing on the screen now for number of us. It's so much always seeing things like this on our screen, especially for those who have their laptop. So this is called the command line. But don't be scared. You're not going to be doing so many things on the command line. But I'm a Linux person. Linux is just like Windows, an operating system. So I love to use my Linux. And we have people who use Linux so well, so they work more on the command line.
That is why you're seeing me working on the command line. So don't be scared if you're not a programmer, if you have never learned to program before. We're going to get there together. Okay, so the first thing I would like to show us
is that when you're going to be installing or when you're doing installation, you need to install Python, which comes with most devices. Even if you check, no, it doesn't come directly with Windows, but on Linux, it does. But you can always install Python directly
on your machine. Once you have Python, then Qiskit works directly on Python. It's built on Python. So Python 3, Python. So once you have Python, how you can know is that you just type Python 3. Then it comes and shows you what you have. For so many people that will be working directly with Windows, so we're going to see together in next lab sessions, not today. Today is just to show you, interact with you, what programming with Qiskit might look like, how the challenges might look like, and questions you might want to ask. And as you take some theoretical talks, you're also going to learn about quantum gate. I know earlier Dr. Diko mentioned some physics to do with quantum gates, and also the use of linear algebra. So all of these we're going to be doing just. So, but then the fun of it is that most of the times when we run code, even if you're working directly on the command line, in a strange format like this. So it's always placed in a way that you can easily access your devices and your notebooks. So we're going to be using more of Jupyter Notebook. So let me go to just to UIQC lyrics. Okay. So I'm working from this folder. So we have all of our materials I want to use today. So I have the Lab 0 from past Qiskit event, IBM Quantum event. So just the introductory lab. And then this year, IBM also, they held the Qiskit Global Summer School 2025. So they gave some labs. So we're going to see them together and then see how the labs are designed. Then we also look at the Qiskit fundamentals, just like you learning to use Qiskit, which we're going to see together in the course of events today. So, but then let me take a quick poll just by raising of hand. How many of us have had? So how many of us have had about Python? You can just raise your hands. Either online participant or physical participant. Can you hear me? You've heard about Python programming, just raise your hands. I can see your hands. Nobody's raising hands. Am I audible?
Not so well. Could you repeat the question again?
Okay, one thing you can do if you want to speak for you should because you're having echo, but can you hear me now? Am I audible now?
Yes, you are audible.
Okay, great. So what I was saying is that I was asking that how many of us have heard about Python before? Just by a show of hands. Okay. I expect to have all hands raised because Python is a very common programming language today. All right, also for our online participants. Okay, but then how many of us have maybe written any Python code before? Okay, great, awesome. So how many of us are beginners? You don't even know what Python is. You've never written Python code before. Okay, all right, great, awesome. Okay, so don't be scared. Python is very easy to learn, and you're not writing the entirety of the code. So I think what you need to learn in using Qiskit is to observe how patterns are written. So I will just do a deep dive now. So
Python has languages the same way. It's a language the same way you speak grammar, English. Then it has the commands to give instruction on what to do. And then it also has objects with which to give your commands. So right away, I'm going to open my Jupyter notebook. You can just do that by typing this and enter the thing. So this will give me a different platform where I can show you the notebook in a more presentable format. Okay. All right. So now I'll begin with Qiskit fundamentals. Just for us to see what Qiskit is about, so we can see it in a more fanciful way. So one of the things that you are going to be learning to do is that people on site, they will assist you on how to install Qiskit on your devices.
Please, are you recording?
Yes, I am. I'm recording. I think recording is in progress. Sure. Yes, recording is in progress. Okay, so I'm not going to cover how to install Qiskit here because we're going to do it just not during the event. There are different videos to use to install Qiskit, but what we're going to be looking at is how to run the tools and what does the tools mean and how do you understand them. All right. So here you are having a Jupyter notebook and you have the cells and then you have exercises. So now this kind of cell, this is the section that you need to now pay attention if you have never written any Python code, if you have never used Qiskit. Okay, so the first line here on this entire cell is calling on libraries to use for quantum computation. So here you have, if you don't have Qiskit installed, then this singular line is going to install all the Qiskits that we need for running events, calculations for this particular forecast. So, but I have it already, so I'm going to comment it out by using hash in front of it, which already tells us that when you have the hash button in front of any line of any Python, it doesn't, the Python interpreter does not reckon with it. Okay. Now, the first line here says import. This is very important because when you do your hackathon or when you want to solve problems, you might be seeing some error, and then you have the challenge of what am I not doing right? Again, you don't need to copy anything from here. This notebook will be available to you. So what is important now is for you to ask questions if you don't understand. Is for you to learn how to, use the notebook itself. Okay, so this first line is importing NumPy. NumPy is a library from Python. It's called the numerical Python. But you observe that you are importing it, then it's using as NP. So it means that the next time you need anything NumPy in this cell, you're going to be referencing it as NP. Is that clear? That's the first thing. So you are calling on NumPy, you want to use NumPy. Whatever NumPy is, we're going to see later. But what this line is saying is that you are importing NumPy, and all those who write Python program understand this. So this is just numerical Python. But the next line is very important for everyone. The next line now is where you are using Qiskit, because it's saying from Qiskit, which is IBM Quantum Information Software Development Kit. So from Qiskit, the first thing you are importing is your quantum circuit. These are the most important part of learning to use Qiskit. And if you miss this, for you to not understand, for you to understand, sorry. So you're importing a quantum circuit. So what does a quantum circuit does? It is with the quantum circuit that you can display a circuit. You can draw a quantum circuit. You can apply gates. How many qubits do I need? So you can, this is the starting point. So the quantum circuit is what you use to initialize your circuit. We're going to see the usefulness later. Then here, from Qiskit, quantum information, that's quantum info, you are importing something else, which now is the poly. They are the poly gates. We are going to see them later for poly operations, sparse poly operators, state vectors. Now, all of these, you're going to understand what they are later, but you just understand that these things have been imported. Sometimes you can be given a task to solve a problem, and the challenge or the problem you are solving is just to import the right tool. Are we following? For our online participants, you have the question and answer column. Please, you can always use it. You can always ask questions using the question and answer column. Your questions will be seen and be answered. All right. So this is the importation. We also import the block bulk motivator. So this first cell, you have to run it for all this importation to be active. So if you are using Jupyter Notebook, which is what we're going to be using more formally, so to run your Jupyter Notebook, there are several options. You can click here, the run button, you say run this cell and advance to the next cell. So by clicking this button, you are running this particular cell only. If you forget to run this cell, please, these are the, for starters, these are basic things for you to pay attention to, because if you are in a hurry, you forget to run this cell and you go ahead to run the next cell, you might be wrong. So here now, here, I want to run this cell. I click on the run button for starters. But then if you are a lover of shortcuts, you should be. You can see that it's giving a suggestion that you should use Shift Enter. Shift plus Enter. So it means that once you are in this cell, you can click Shift, then Enter. It will run the cell. So you hold the Shift button down, then you click Enter. Are we following? By a show of hands, how many of us are still following? Okay, great. All right. So I'm running this cell now. So one of the things you should observe now is the star button here, the star icon. This star shows that now it has changed to 1. Do we all see that? Did we all see what happened in this bracket, this section here? I'm going to rerun the code again. So observe how it changes. Initially, it was empty. So let me restart, because these are things, basic things you pay attention to. Now look at the bracket. Now it is empty. Can we all see it? One moment. Can we see the bracket on the left? The rectangular bracket. Now it is empty. Nothing is in it. So if you scroll through the notebook, you can see an empty bracket again. If you scroll through an empty bracket, in the Jupyter Notebook, it means that that cell has not been executed. That means you have not used the cell. You have not, in the context of programming here now, the cell has not been executed. So you have not clicked the run button for this cell. So it's one way to check. Maybe you thought you have click the run button, but you did not. So once I click the run button, I want you to observe the transformation of this bracket. Now I just did. Now it's transformed and changed to 2. It was faster than earlier, so I want it to be very slow. So I'm going to start again. So I'm going to interrupt the canal. Stop it. And then now, okay, great. I'm starting again now. So I want you to observe how long it will take before something appears in the bracket, and then to see how it changes. This is very important. So now you can see a star. The star changes to 1. Did we all see this? Okay, great. So when you saw the star, it shows that the code is being executed. So you have to wait for the execution to complete before you can have the results of your execution. So by showing 1 here shows that this is the first execution that I have done in this notebook. That is the number 1 that I'm seeing. So if I scroll up, I cannot see any other number. So I'm only seeing number 1, which means this is the first cell I executed, and it has been executed. This is number 1. It has no output because I'm not seeing anything new after the execution. But what it means is that it has been executed, and it is the first one to be executed. So I can move on with the information I have next. So now here is telling us about single qubit operators. I know in the lecture you had just now, more people are still coming to tell you more about the operators. So there are X gate, Y gate, Z gate. In Qiskit, they are referred to as the Pauli operators. For those who have studied quantum mechanics, you must have heard about the Pauli gate, the Pauli operators. So here we have the X gate, the Y gate, and the Z gate, and the identity operator. That's the I. So you can generate them, and also you can generate them from Qiskit directly using the Qiskit quantum circuit library, or you can use the Pauli operators. You can create how they should behave. So here now you can see what is next here. You have to write codes that perform the following functionality. First, it's going to create a 3-qubit Pauli operator representing Z on qubit 2, Y on qubit 1, and identity on qubit 0. Then what you have to do is to print the operator. Then the third thing is to print the corresponding matrix representation. What all of this means, you should not bother by now. We're just seeing an example of how to use the notebook. So it means that if you understand this exercise, what you are supposed to do, then you have to supply your answer inside a cell like this, where you see your code here. So you have to put your code. You can ignore that line and put your code in the next line. So maybe you understand what to do. If you do, then you can say, I'm to create a 3-qubit Pauli operator. Maybe I'll call it 3-qubit. I'm just trying Pauli operator up. Then I say, I'm dividing to be equals to something. If you understand the exercise, this is how you start. So you want to define the operator, you write it out, you give it definition, then you have to print the operator. If you have used Python before, all you need to do is just to do a print, then of maybe the name of the operator you want to print. It's not a string. All of this we are going to learn, so don't I'm just trying to show us the approach to answering the question. So I'm printing it now. Maybe I have to print the corresponding matrix representation. If you understand the question, there's a way to print it. We are going to learn all of this, but this is just how to interact with the notebook. So you put in your code. If you are done, just for example, I'm just doing something that is not correct, but might look somehow correct.
I will just call it Z2 Y2. So I'm going to say ZYI. Suppose this is correct. I'm not saying it is correct. So then you print your code, the matrix representation. If it has a matrix representation, then you run it to check. So if you do, now I have executed in the cell, then you have number 2. Whether this is correct or not, I don't know. But the fact that I do not have an error means that I have written something logical for Python to interpret, for Qiskit to understand. So there are 2 challenges when you write your code. The first challenge is for you to write what is interpretable, what Python understands. The second challenge is what you have written, even if it is interpretable by Python, is that the required solution? Do I make sense? I will say it again. The challenge when you are writing your code, when you want to answer the question, the first challenge is for you to write an interpretable solution. What I have done simply now is an interpretable solution because Python has no issue with my syntax. It has no issue with what I have done. Then I have a code that runs with no error. I should be proud of myself. But the next question is, what I have just done now, is that the required solution? Are we following? So whenever you have a challenge like this, you have these two things to solve. The fact that your code is being executed, you say, wow, I did it. No. You could write an interpretable solution, but not the required solution. So in most challenges, the ones I've attended with IBM, so IBM requires you to put in codes in some missing places in their notebook. You can put in the codes and you have no error. But IBM will then check from their own solution check whether the solution you have provided is the correct solution. So as we train ourselves in using Qiskit, this is the challenge. First, to write an interpretable solution. Then, to ensure that the solution we have written is the required solution. Is this clear? So, writing an interpretable solution is from your understanding of Python language. Number 2, from your understanding of Qiskit documentation. That is, the developers of Qiskit, they have written how Qiskit should be used, which we are going to learn. So there's nothing to panic about. If you have never used Qiskit before, that is what I'm doing here, to guide you through how to learn to use Qiskit. While in this alongside, we are learning how to write Python codes, because Qiskit is built on Python. It's the same way you go to class and say you want to learn mathematics. Mathematics, of course, we are in the department of mathematics today. Mathematics has always been taught in English language, at least so far, except for some lecturers who want to be indigenous and they speak to you dialect. But you realize that even what I am doing today, I'm speaking in a language that everyone already understands. Understand. Then I'm using that language to pass across information. Python is a language. Every programmer, any programmer who writes in Python understands the language of Python. Then the challenge now is to use this language to give meaningful information. So an error in Python generally will be to do something like this. I add a quotation mark at the beginning, then I never ended with a quotation mark. This is an inherent error in Python. And as you can see, I'm going to run the cell again. I can see immediately an error. And Python is very interesting to learn. If you understand this stage of Python, it is the first thing that will save you in writing any code. Now you can see my number has changed to 3. Here it was 1. So this gives me an historic record of what I have been doing. By checking number 1 here, and the next cell, I'm seeing number 3. It tells me 2 things. Number 1, it tells me that I have done 3 executions so far. The second thing it shows is that because I have number 1 and I cannot see number 2, that means that this particular cell, this is the second time I am doing the execution. So it has overridden number 2. Does this make sense? Because if you have an error and you want to show people and say, oh, I have a problem here. By checking the history, we can tell, oh, that means if I can see maybe 25 here, that means you have tried over and over again 25 times. Even when you are submitting your solution, things like this count. So what is the challenge? Python is giving us an inbuilt solution or information about the error. It's saying that there's an unterminated string literal. That is, it's even showing me an arrow to hint me where the error is from. Are we getting this? I know our Python scholars, this should be boring to them, but we have to take things gradually. Are we following? So when you see an error like this, first understand the comment Python is giving you. The first comment here is telling you that in 3, that is this 3, cell 3 is giving me what I am doing. Can you see cell in input 3? So this third input that I'm seeing here, line number 2. That is, if I count the line inside this cell, line 1 and line 2, exactly what is on line 2, Python reprints it for me. That this is where your error is from. And what is the error? It's giving me a hint of an arrow here. That check this position. Something is wrong from here. Are we following, please? So from this point, you should have concern about the error. So I check that point. Oh, what is the problem? What could be the challenge? Then it's giving me information. Unterminated string literal. It means in our normal language, I started with with a quotation mark, single quotation. I did not end with the same quotation. That is what Python is trying to tell us here. It is a Python problem, not Qiskit problem. So if I go back to the code and include the required syntax, and I try to run it again, now it is interpretable again. I will do another one because these are the errors you're going to face when you are solving problems. So it's good to start with it. So you say, I've tried that question number 2. It's just giving me error. So you should know what is the error. Okay, so now let's look at another challenge. Now we have an error. So let me ask, can someone tell us on what line is the error in our code now? From what Python has suggested. Who wants to answer? Either our online participants or because these are the basic things we should start with in learning programming. Yes, do we have anyone? Where is the error? On what line? Yes. Everybody knows the answer, but nobody wants to answer. Interesting. Okay. It should be
The error is the letter.
on what line? The code has 3 lines. Line 1, line 2, line 3.
That's line 3.
Line 3. Awesome. Great. Line 3. I don't know if our online participants can unmute themselves. Let me quickly check this. One moment.
Yes, I did. I unmuted and I spoke.
Oh, okay, great, great. So line 3. So Python is already suggesting to us the answer. It is here. Are we following? Line 3. So this line 3 is where the error is. Python will tell you automatically. And even beyond telling you, it's going to show you the content, which is what is here. That check this line 3 very well. This is where the error is from. That is what Python is saying. Now, if you don't even know what to do, Python is giving you a suggestion already. That's the last line. So it's going to tell you where the error is from, and it's going to suggest what the error is. So it's saying that name 3 qubit O is not defined. Of course, I have 3 qubit OP. But when I wanted to print, probably anxiety or because I was absent-minded, I forgot to type the name correctly. So I omitted the P. Now Python is saying, I don't know this name. This is 3 qubit O, but the name I can reckon with is 3 qubit OP. So Python is not telling you the name to put there. But Python is only saying, I don't know this name. Please, what are you telling me about this name? So that is where the error comes from. Please, as far as learning to program is concerned, I believe if you understand this part, you have your problem half solved. I remember when I was learning to program also, this was the first thing I learned. Even without learning to program itself, you should know where you are doing the wrong thing. Because once you know where you are doing the wrong thing, it's easier for you to find the solution. So it's not just saying, I don't know what is wrong. I don't know what is wrong. I'm just having error. Because in a few days, such song will be sung. I say, are you done with your first task? I was trying it. I spent 3 hours. I don't know what is wrong. I was just getting error. So we want to avoid that from the start. We want to equip you with knowing what is wrong. I think if you know what is wrong, then you can solve the problem. Either to search correctly and, okay, what can I do? What can I change? And this is how you are learning to program. I will also say, yes, AI tool is good. ChatGPT is awesome. But if you are starting out in learning to program, it is not advisable for you to ask for solution. What is advisable for you to do as human is to know the problem. When you know the problem, then you want to solve the problem. So solving the problem can involve the use of AI tools. I hope we are learning. So you can use AI in solving the problem, but you have to ask the right question, which shows that you need the solution, but you have to understand the problem. Because when you are in the real world, you are solving problems. You are going to be employed, you are going to be having internship in any organization to solve problems. So you either to find out what the problem is in certain area, and this is what research is about, then to prefer solution. Okay, all right. So again, if I'm to correct this, I just go back and put the required name. Another thing that happened is this. Sometimes you have gotten an understanding of the error, but because of anxiety, you want to put the correct solution. Then in doing so, you make another mistake. Then it gives you the same error. It might look the same, but they are not the same. Because now Python is giving you another error that again, the name 3 qubit OP is not defined. But you feel like I just corrected it. The error now is that the P was supposed to be in lowercase. I know people that have struggled with solving errors will understand what I'm saying. It looks quite simple, but these are where challenges come in. So the error now is because you are using the uppercase P and not the lowercase p. So I changed it. I put my lowercase p. Then it is okay. The fact that you are able to solve this error, even if it took you 5 hours, the next question is this the required solution? Okay. I'm not saying this is the required solution. I'm just taking you through how to use the material. When you have questions, when you have challenges, by the time you start the hackathon, by the time you start to solve problems, you're given materials to complete the codes in them. All right. So here again, you are given an exercise. You have to create a circuit that contains 1 qubit. Okay, for my own knowledge, you can just try to say, okay, now you have quantum circuits. You have called it before. Quantum circuit. Where does this come from? What quantum circuit comes from? You will see it again from the first cell here. So I just my hello. Can you still hear me? Show of hands from the physical participant. I can see you more.
Yes, we can hear you.
All right. Okay. So here we imported the quantum circuit earlier. So now I'm using it for the first time in cell in this new cell. So this code will work because I have earlier imported. So let me run this now. So this works because quantum circuit now is known by this notebook. It is from Qiskit. It's something that comes directly from Qiskit. So it works because this cell 1 that seems to do nothing earlier has already imported the quantum circuit into this notebook. Let me show you an error that can happen. I'm going to restart because these are the basic things I want to do in this session. I want you to give you the introductory part so that you can be fortified to work with materials on your own. This is the goal. So if you're not taking anything out, please ask questions if you're not getting anything. So I'm going to interrupt the kernel again and clear all the outputs. So what could go wrong? I would tell you for free that now I have not done any execution here because it is now empty. Then you would realize that this code will run without any error. Why? This is an inherent Python code. It has nothing to do with Qiskit. So that is why it works. But by the time I get here, quantum circuit that I'm using here is from Qiskit. If I run this code, even though it looks okay earlier when I did the calculation, now it is giving an error. And what is the error? It's saying quantum circuit not defined. So that means this notebook does not understand what quantum circuit is. And this is the reason for importing the quantum circuit library at the beginning. So sometimes when you look at all the things you need to import, if you have good knowledge of your operation, you import them ahead of time, but this is not necessary. But in practice, this is what is done by professionals. But you don't have to do that for starters. So, but we know ahead of time all the importation that will be necessary. Part of your challenge can be that you should import something. So don't think that because you have a list of importation here, all the importation has been done for you. No, it could just be the essential. It could be part of what you are going to be tasked with. Are we following by a show of hands? Okay, great. Great.
Question. Can we import at the point of use?
Sorry, there is an echo. One of the reasons you have an echo is that you have two devices and both have the microphone on. So one is picking the sound from the other. So what you can do is you turn off the sound of one of your devices. Just turn it off, or you mute it, not from Zoom, but from the system itself. So mute the sound from one of the system that you are not using for voice. Okay, I think you can talk now.
Can we import at the point of use in the
At
cell?
the point of, yes, this is possible. Now, this is one of the solution. Now the error says quantum security is not defined. I say, oh, I've not imported it. Now, if Qiskit is installed on your machine, what the solution will be import. So now I will have to call on Qiskit. I say from Qiskit, oh, I have not imported quantum circuit. Then I say from Qiskit, import quantum circuit. I'm going to do something again, which is not the solution. This is the solution to this error. But what I'm going to do, which is common from my own previous mistake, now I know that the solution is to import quantum circuit. Now I'm telling Python, import quantum circuit. If I do this, it leads to another error, saying that, yes, look at the line. The error now is on line 3. You are asking me to import quantum circuit, but I don't have it in my package. This does not come directly with Python. It is not a Python-owned module. All of these things have their meaning, but just for you to know the problem and the solution. So then what do you need to do? Have I installed something that has quantum circuit? Yes, that is Qiskit. Sometimes in some materials, in some notebook, you are using different modules. Say, for instance, because you are a quantum computing researcher, you are using Qiskit, at the same time, you are using Penny Lane. Penny Lane is from another industry. So if you need to work with both in a particular work process, so you have to import their material, their libraries differently. So now I know quantum circuit is from Qiskit. So I say from Qiskit, these are Python languages. So this works. So from Qiskit, import quantum circuit. And once I do this, I don't have any error again, because I've installed Qiskit on my laptop. If you are yet to install Qiskit on a laptop, this will flag an error. And this is why we need to do Qiskit installation on our own personal computer as we progress. Are we still following up onto this point? Okay, great. How much time do we have left? I think we have an hour left. So this, now we know to import, we're looking at the error, we are trying to correct them. But in this question, create a quantum circuit that contains 1 qubit. Now, I know there's a quantum circuit. Please, this is the next thing I want to talk about now. I know there's a quantum circuit. Then the next thing is, how do I create a quantum circuit? To create a quantum circuit is just for you to call on quantum circuit, just like I did here. But then the question is, how do I use it? And this is where documentation comes in. I think last year I did a little introduction on the use of documentation. So this is the most important part of working with IBM Qiskit. So you need to go to IBM documentation. I'm not going to do so much of emphasis here. You go to the documentation, so you work hand in hand. So I say Qiskit documentation. Qiskit documentation. This is the document that houses all the libraries that Qiskit that has been written into Qiskit. So this is the documentation. Then I can ask, what am I looking for in the documentation? So I can say I'm looking for quantum circuit. So map problem to quantum circuit. These are all different workflows, but generally I can just go to guides or come to anywhere. So these are the documentation guides. People who invest a lot into doing quantum computing research, this is their own study house. So they come to learn, okay, how was Qiskit designed? So they told us, so this is circuit and operators here. So you can see on this left side, construct circuit. I click on it. So it's going to teach me
How do I construct circuit? So this is a guide. Are we following this? So this is a guide that can show you how to use your code. So how do I construct a quantum circuit? You can see just what I did earlier from Qiskit import quantum circuit. So this is already a solution. So this is what you do with ChatGPT. So ChatGPT goes to documentation on your behalf, studies the documentation and pour the answer to you, and you're like, wow, I got it easily. You are not learning to solve problem. If you know where, so this is also an expo, which is allowed. But this is the proper way to get things done. So the process of you looking for the answer, you know the problem, you know what you want. You know you want to solve it. So you know where to go to. These are the skills that no AI can give to humans. Knowing who to go to for the right solution. So if you are developing something that is innovative, nobody has done it before. So where can I probe to get answer? And this is what gives intellectual solution. So here you come to the documentation. There's a guide. A guide is just to show you a sample. That's what a guide is in this case of Qiskit. You can also go to the code itself, the syntax of the code, which you don't need, at least for this introductory level. But a guide is the best. Are we following, please? So I come to the guide. How do I get here? Let me do that again. You can just go to Google. You click on, from Google, just search Qiskit documentation. Once you do, you click on IBM Quantum documentation. Once you have done this, now you have, do you want to read the documentation itself? When you get advanced, you see what your documentation could do. But do you need guide? Yes. What you need is a guide. The same thing you do by asking or trying to copy from someone and say, how did he do it? This is where you can copy from. So you go to the guide. So when you go to the guide, the next thing is, do you know your error? Do you know the problem? The problem is I want to construct a quantum circuit with Qiskit. Oh, then you go to circuit functions. It is here. So when you click on circuit function, introduction to Qiskit function, here, under the guide, tools, okay, you come here, this is here, not what to do on the circuit. This is the circuit itself. So now circuit library, the one I told you earlier about quantum circuit that we called, if you remember earlier, we said from Qiskit called on quantum circuit. That's the circuit itself. But now how do I construct the circuit? So this is it here. This is the guide. So to construct a circuit, all you need to do is that you call on the quantum circuit, which I've mentioned earlier. Then you name your circuit. This is QC. QC is not cast in stone. You can name it anything, as we're going to see later on. But to make things easier for you, in your own task, the guide will come with the notebook. That means you don't have to come to Qiskit documentation to look for the guide. The guide you need will directly come with the task. So the idea will just be, what do I need to change? How do I need to use it? And if it happens that it is not in the material, then you can come here. Because this is what will show that you really learned to use Qiskit. And I hope that in the nearest future, you can tackle some IBM challenges on your own. Okay, so now how do I create the circuit? I come here, I say QC equals quantum circuit 2. Now, the question here is that this does not tell me what it means, but when you read, it says the following cell create a new circuit with 2 new qubits. Now, this is a guide. It doesn't give you all the answer. And that is why the documentation gives you the structure. That is, if you know how codes are being written, then the documentation gives you the structure. And this is where I am now. This is the quantum circuit class. You don't need to bog yourself with so much of details once you know it already. So in the quantum circuit class, this tells you what to do, how the whole program was written. Okay, So now this is the quantum circuit that you call. So now I'm going to write to show you what I'm saying. Now, I hope that you can see what I'm writing now. Can you see? Okay, great. Now, if you create your quantum circuit, just like you have it here, quantum circuit. Now, I open a bracket and I close a bracket. So the opening and closing of this bracket is what you have here and what you have at the end here. So what you have in between are the different options that Qiskit quantum circuit allows you to provide in the event that you need to do so. Are we following this? So everything in between open and close of bracket is what you have here. But for simplistic state, now, for simplicity, you don't need to provide everything. So from here, name has been provided for you as none. That is, if you don't give it any name. The global phase, you don't need to worry about it. It has been given for you. All of this has been provided. But the most important thing that must be provided are your registers, which is what is here. So what all of this means, we are going to get into it one after the other. We are not trying to rush ourselves. So what it turns out to be is that if you look at the usage here in the guide, I circled now, you have only one thing in the bracket, which is just the number 2. So now the questioner is, when I have one thing in the bracket, what does it mean? This is now the next question we want to ask ourselves. Now you will see here, as I scroll away, you will see here that what the information means is this. When you have a quantum circuit and you provide information to it, the information has what it means. Because here now you have an example where you have 2 different information. You have 2 and 2. Ideally, for us not to take so much time, what it means is that whenever you have this quantum circuit object can create for you a quantum circuit that has quantum register and classical register. Quantum register will store the qubit and classical register will store your classical bits. So for example, you can always provide a number of qubits that you want, and then you can also provide the number of classical bits. By doing it this way, 3,1, so I'm asking to let me show you so that we can have a good feel of what we are doing. So I'm going to come back to this, and these are the first steps in quantum circuit divination. So here, the results, X is 3D. Yeah, I'm having different versions of Matplotlib. Okay, so now this is what I just did. You can ignore the warning. This is just a warning. I will have to silence it later. So just from my own end. So now I have Q0, Q1, Q2. These are the 3 qubits I have just produced now. But then I produce alongside with it a classical register that has 1 bit in it. This is the one. This will be useful for measurement as we proceed. So for me to produce a quantum circuit of 3 bit, let me remove the matplotlib option so I can have easier solution. So here I have just the 3 bits. It's just showing as a form of Q0, Q1, and Q2. It's just to make it fanciful. That is why we always give the matplotlib option to give us a fanciful design, which is what you have here. Are we still following? So that means that whenever you call on quantum circuit, the guide shows us that when you write this way, you are producing a circuit that has 3 qubits. If you don't have anything beside the 3, like no comma for any, so you don't have a classical bit. So you cannot directly measure into your classical bit and find the solution. So here you can create 3 qubits. So, but let's go back to now for this kind of question now, I have created a code that is Python readable, number one. Number two, that is Qiskit interpretable. But the third question now will be, is it the required solution, which is the same question I asked earlier. So now we have two stages of error now that we can have. You can have an error that comes directly from Python. You can have an error that comes from your use of Qiskit. So for instance, if I do this, I know this doesn't make any sense. I'm providing 3 options into the quantum circuit module from Qiskit. This will not make sense to Qiskit. Now, you can see it gives me a lot of stories because this is coming from what has been encoded into Qiskit. But then you don't have to read all the whole thing. What you need to read is where is the line of error and what is the suggestion you are giving. I cannot over-explain this. If you have an error, 2 things are important. First thing is, where is the error coming from? In this question, it's telling me the line 4. Immediately it gets to line 4, it sees the problem. So what is on line 4? It prints it out for me. This is where the problem is from. Of course, I deliberately did this. It could read my mind. But then the question is, what am I doing wrong? Then you go to the very last line. Don't bother yourself to try to understand what is within this error line and the last line. It is not for you. So what is, of course, if you understand developing of code, when you get to that phase, you can understand it. I'm not saying you should not try to understand it. But here in the last line, it's telling me that what is referred to as quantum circuit from Qiskit can be registers or integers. It's giving you what it is designed to do. This is what developers do when they write code. They give this kind of error information that once there's an error, what should the reader see? So they have given us hints that what we are trying to do can only contain register or integers. Integers are whole numbers. So that means if you try to put 2.5 in that bracket, it will also give you an error. Now it's saying the integers it can take is only up to 2 arguments. So don't provide more than 2 things. This is what you are learning in this event. You can use it anywhere outside Qiskit once you understand the syntax of error. So up to 2 arguments. So don't give more than 2. When you are solving problem with Qiskit and you are using this particular module, do not provide more than 2 integer arguments. If integer now, as you can see, if what you are providing are integer, only up to 2 arguments. So if you meet someone that says, I'm a software developer, these are one of the things that they do. Some software are badly developed, such that they don't give this kind of good information when there is error. So if you are aiming to be a software developer, these are where you are needed. So things you need to write for the users to see even when there's an error. So it's not telling us that quantum circuit was called with 3, 2, and 4. This is not in line with what it was designed to do. So because we are providing integer, we cannot provide more than 2 inputs in this circuit if we are providing the integer. So I will only provide 3 and then 2. But what does the 3 and the 2 means? The 3 is the number of qubits that we have, and the 2 is the number of classical bits that we have. So the draw option is, I'm just drawing it to show that what I am doing, I want to see it in pictorial form. But now, let's now look at another error. Another error, this is a Python error, not Qiskit error. So that is why you don't have so much of a story within it. So it's just telling me that, again, I had a quotation that I opened, I did not close it. Then you go back to close it. So these are challenges you're expected to be able to solve on your own when you face them. So that when you are asking the people on ground to assist you questions, you are asking reasonable questions. So they will be there to guide. I will also be available to support if you have questions. But if you ask questions that you should be able to solve, then you are not doing the right thing. So now our code is readable. Then it means it is Python compliant, naturally. Then it is Qiskit compliant. The next question you now ask yourself will be what? Is it the required solution? I hope you're following the flow of the information. So the question says, create a quantum circuit that contains 1 qubit. So can someone tell us if this is the required solution now? Anyone? Volunteer? So this is a Python compliant solution, Qiskit compliant, but is this the required solution if you are asked? This number 1, to create a circuit with 1 qubit? No, right? Because this circuit has how many qubits? Yeah, I can see the participant. If you want to show me, you can just maybe talk, or you can just 2. Yeah, cool. Somebody says 2. It's not 2. It's not having 2 qubits. It has 2 inputs. Yes, is someone responding? Yeah, you can just show me with your fingers if you are physically there. Okay, great. 3. Somebody answered. It has 3 qubits. So to correct it, then you come to where you have your qubit number to be 3 here, you change it to 1. Now, I seem to have a reasonable solution, but this is also not the required solution, so to say. Of course, the draw part is not part of what I'm trying, because by the time you are doing your hackathon or the challenge, these are the things that will be checked. Or maybe you're doing an online program and you're asked to solve your problem in the Jupyter notebook. Now, this solution passes, at least for some easy stage. Why it passes is that the checker or whoever is checking, they check either strictly. Sorry, one moment. So they check either strictly or just fairly to show, oh, is this what is required? Yeah, this is what is required to create with 1 qubit. But in addition, you have created with 2 classical bits, which is not required. So oftentimes you just stick to the actual question. So with this alone, you have the required solution for question 1. So with this, I have successfully solved this. This material will be given to you. You can practice with it. You can also check the solution. So you're going to be given both the material with the question and the material with the required solution. Are we getting this? So you can practice through with it. You check the required solution, then you check your own solution. Are you doing the right thing? So, but the challenges will be given to you without the required solution. So it will now be your own task to put the required solution into the missing location. Okay, so I want to be faster now. So this is how you create 1 qubit. So I believe by now everybody can create a quantum circuit with at least a number of qubits. Is that clear? Okay, so now the second question here says put the qubit in state 1. By default, these are information you need by learning Qiskit. By default, when you create a circuit, a quantum circuit in Qiskit, by default, all the qubits are in state 0. I know you must have been told that qubits can be in ket 0 or ket 1. So by default, when you create a quantum circuit like this, all the qubits are in state 0. So now you are given to write a function or a code that, first of all, create a quantum circuit that contains 1 qubit. You have done this successfully. The last part is not necessary. You're just showing it to give yourself a check whether you're doing the required solution. Now it says put the qubit in state 1. Now this is where you begin to learn more of how do you now manipulate your circuit. Well, the solution is not far-fetched. It's just for you to manipulate. Now the circuit, everything in the circuit has been assigned the name QC. So this QC now, based on the way it is written, if I want to manipulate it, I just call the name QC. If you see the last line, I just did QC.draw. Then I put in brackets something. It's saying that draw this particular quantum circuit. So now if I want to manipulate the circuit before drawing it, now one of the things that can also be like error is that, oh, you have done the right thing, but in trying to check, you did not check correctly. Because now I withdraw, but it's not going to show me the last thing. Because now Python reads line by line, and it only gives me the output of the last thing I've written. So the last thing I've written is Qiskit, and it has done it. So again, what I'm going to do now is that even with what I have now is still this, then to put it in a state where I can swap the qubit, it means that I want the qubit to be 1. So I use the S gate. This we are going to learn gradually if you have not. So I apply the poly X operator. You know, initially the first question says I should create a poly. This is not correct. I don't want to take you through creating it. You're going to see how to do that gradually. This is just to show us how to run the notebook. So here, this is directly from Qiskit. This is the X gate. So the X gate is a small letter X. How do I use it? So once I call on the circuit I want to modify, which is the QC, then I call how to modify it. I'm saying apply S gate on what qubit? So I have only 1 qubit in the quantum circuit. So there's nothing else I can do than to apply the S gate only on the 1 qubit that I have. But the way qubits are counted in Python, or even generally counting in Python, starts from 0. So your first qubit will be qubit 0. Let me show you one thing again before this. Suppose I have 3 qubits, which is good for our explanation. You will see that already the qubits have been numbered for me so that I can really reference them. So this is qubit 0, qubit 1, qubit 2. But because I have only 1 qubit, it does not stress itself. The people who develop it do not stress themselves to be labeling it again. It's only 1 qubit. So there's no point of qubit 0, qubit 1, or qubit anything. Are we following this? Okay. So, but for the sake of our required solution, I will just do qc.x on the first qubit, which is adding the 0 in it. And you're going to see that the S gate appears directly on that qubit. So suppose I have 3 qubits again, just for explanation, and I apply it on the first qubit. Only the qubit 0 has the S gate. So I can tweak it to say, okay, let it be on qubit 1. So qubit 1 will now have the S gate. I can say, let it be on qubit 2. Sorry, I will use first, second, and third. So first is 0, second is 1, third is 2. So on the third qubit, then I put 2. Then I have this. Somebody's already thinking, what if I want to have it on qubit 0 and qubit 2? So now it takes a step-by-step approach. You already know how to put it on each of the qubits. So do it one after the other. So you can say qc.x, first put the S gate on qubit 0. Then once you are done, put another one on qubit 2, and you have your response. Done. So this is how you're going to be manipulating the circuit until you design the required circuits. So sometimes some circuits can be so complex, but you're going to start. So this is why quantum computing is at the stage of qubit by qubit manipulation. It's a very crude way of computation. Classical computer has gone beyond this. We are now giving logic gate instruction where we now have IC. You now have IC that can do so many things by just tapping buttons. So when you pick up your TV remote and you click next, it seems as one single operation. It is not. It is millions of operations like this that has been done within a compact form. So, but in the stage of quantum computing, especially with Qiskit, you are going to be doing qubit by qubit manipulation. Although there is an advanced way to do manipulation of more qubits at the same time. So you have technologies that are designing, people that are designing this in their own technology. But this gives you like to see the fundamental thing. So far, I've been able to create a circuit with 3 gates, add X gate. So what other gate can you think of? Maybe the Adamad gate that you have always been seeing is H, is represented as H. How will I know it is H? The Qiskit guide will tell you, or the documentation. How do I know what to add to it to get this? This is where your guide comes in, or experience. Now I just wrote H there because I know that from experience it is H. I have the knowledge. So now I see the Adamat gate instead of the X gate. And all the things you'll be seeing as people give talk, Adamat, Z gate, Y gate, you can easily implement them on Qiskit. And this is what we're going to be doing together more and more as we have more lab sessions. So this is what the lab session is about. So you enjoy it more when you can run them on your own laptop. You are seeing the diagram as you are seeing it on the screen now. You are the one, changing the gates the way you like, and then that will be very fun. That will be much fun. So now to go back to the actual question, this is not giving any error, but it's not the required solution. I hope we all understood this, because you have to just get one gate and one qubit and put it in S gate. So this is more of what the lab sessions will look like. This is what we're going to be looking at: different problem, different solution. How do we approach them? Just to take you through the solution process. Then when it is time for you to do the calculation or to do your own computation on your own, then you can do it. So the draw, it's good for you to draw your code to see if you are making sense, especially if you understand the circuit. All right, so I'll be ending this shortly so that I can have room for question, and then also take different question if there are any. Then here you add a single gate to the circuit. Now this is now something else. You have to, the question number 3, you have to add a single gate to the circuit that applies the pi/4 phase shift to the qubit. Now, what does this mean? There are more contexts, so you use the rotation gate, because phase shift is just rotation. You're going to see all of this from those that are going to give you theoretical talks, and in the next 3 weeks, I mean, things like this will just be things you can easily do with fun. So to do that, so I can just say, okay, maybe I've done part of the work for you. I can say, enter your code here for the rotation. Then you come here to complete the task. So this is how your task is going to look like. So there are tasks that has been solved already, but it's just for you to also, take yourself through the procedure of solving the task and finding out that you gave the right answer. Because as we're going to be having more events, IBM is going to be organizing more of these challenges, and it will always be nice that you know what they're asking you to do, and you can actually complete the code. Okay, so this is not complete because you need to apply the RY gate to rotate it and give it in phase 4. Some of these phases you cannot see them. So even when you have applied the gate. So another thing you can now see is to see the Dirac notation representation of the circuit state vector. Earlier, I recalled that Dr. Diko gave us a talk on the Dirac state, how it can be represented. All right. Then again, you can do block sphere. You can check it on the block sphere. How does it? I was explaining RY, RX, RZ earlier. So you're going to see these are gates. These are tools that you have directly on the Qiskit library. So these are just fundamentals, things you can learn to do. Don't worry, this notebook will be given to you. I'm going to share the link they're going to share the link with you. Then you have the notebook, and you also have the solution. So that means you can check while you are working. You can, what do I need to do here? So just to familiarize yourself with the platform. So you can copy directly the solution, put it in your own notebook, and see what it does. So, but ensure that you follow the flow of the whole procedure. So from the next lab session, this is what you are going to be doing. So the only assistance you get is when you have error that you cannot solve. So you are going to be with your own laptop fighting with the material. Then you have the solution already, but you are trying to now make it work with your own machine. Or sometimes you are giving the material ahead of time. Then maybe 2 hours later, you are provided with the solution, so that at least you can have some time to go through it yourself and see if you can solve it on your own. But for the first lab session, you are going to have both the material and the solution. Do we all get this? So that at least you can play with things and see how it works. You can see how you can make error just by typing the solution. You already have the solution. Now you want to type it into your own code. That can lead to error on its own. Say, but I copied it correctly, and you are seeing it. Maybe it's just one equals to that is missing. Then Python will tell you, oh, you have missed the equal to, you spelled it wrongly. So these are things that you familiarize yourself with before your main challenge. So don't be scared. They are simple things. So it's just for you to prepare yourself ahead. So I believe now I'm going to stop sharing my screen to take questions. And then before then, I also want to show us a typical challenge. This one, the cells looks very empty, but here you have half code, then you need to put in. So this is the Global Summer School challenge. You're going to have this also, you're going to have this lab. But when you have this lab, this is the one I told you that you're going to have the lab, then you are going to get the solution like hours later. Now the solution is readily available, but we are here to learn. So just learn with the approach that we have. So here, this is the original lab that IBM gave this year during the Qiskit Global Summer School. There are 4 of the lab, and they increase with increasing difficulty. So lab 0 is the simplest one, and it's very easy. And sorry, 1 minute. Yeah, sorry, I had a call. I'm actually done because I just want to show you how the actual material looks like. So this material guides you into the solution. So if you study it properly, you should get the answers from it. So they are not trying to give you something very tough. You have the details there, you read. So this is like a typical way it is, but the fact that the material guides you into the solution does not give you the solution directly. So sometimes you have to use resources, like you can see here. Furthermore, so like let me show you. So here it says the hands-on component of this school series of Jupyter notebook designed to guide you through different topics of interest. Then each lab complements the corresponding theoretical lectures that was given during that time, and include helpful links to documentation. As you can see, again, they are referring you to documentation, to tutorials, to references, to the lectures itself. Then you can also use the IBM Quantum Learning Platform, which we are going to talk about within the course of the event. But just for me to round up, so the lab 0, which is this lab, we are going to get it later. So here in this lab, we are given a means of installing Qiskit directly. How can you install Qiskit? So here, this code is for IBM to check whether your solutions are correct or wrong. So here, you have the grading material to grade your work if you provide the required solution. So here, this is what makes the challenge very interesting, because sometimes you have your own way of getting the solution, but they want you to get the solution in a particular way. So, and this is what restricts it and makes it a challenge. So you have to know or understand how they want you to give the solution. So here, for you to install Qiskit, you can just install Qiskit directly. And there's also something about running code on IBM machine directly, because IBM has quantum computers that has been built. So for you to do this, of course, in the course of our event, we may not need to do that so that we don't get to complicate what we do. So you can run all the code directly on your laptop. But in the event that you need to run on IBM physical computers, you need an account with IBM. And if that will be the case, we're going to guide you through how to do that. And they give you like a free subscription for some minutes, because you can't just be submitting whatever on the computers. Okay, so here, this is how to create an account. So when you create an account with IBM, you have some of this platform. You create API key, you copy your key, then you come to paste it here. So this is the first task. So it's not really a task, but you should be able to do this. So here you can see the int, delete this and paste your API key here. So you delete this, you paste your own key. In trying to delete and paste, you can delete the quotation and it gives you errors like, it's not working. So you should be able to solve problems like that. But where the work starts from is here. So here you can see again, they made some importation, which should make sense to you now. Then sanity check. Sanity check is to check. So let me run some of the codes so that we can check what is going on. So this should run successfully. This should run successfully. I don't have an issue. I don't want to install. I already installed. This should work successfully. Then I don't have an account. I'm not doing anything on the account for now. So here, IBM runtime, I run this. I'm trying to import unnecessary libraries. And then this runs successfully. Now this is a sanity check, just to check whether everything you have imported runs as expected. So now what they said here is that you are creating a new circuit with a single qubit. Now create a new circuit with a single qubit. Now this is QC with 2 qubits. So this is not correct. It can be a single qubit with 2 qubits. So with 2 qubits, then add a H gate to qubit 0. So this is the task. So to do that, I believe I've explained this by now. So you do QC.H, qubit 0, just put the 0 in. Then add a C0 gate to qubit 1. So C0 gate, you're going to hear about the gate. So now to add a C0 gate to qubit 1, controlled by 0, because C0 is a gate that works on 2 qubits. So you are adding the C naught on two qubits, qubit 0 and qubit 1, but you are saying that qubit 0 should control qubit 1. This has their own implementation. So now it says, what do you have? So this is the design that we have. So you can easily interpret the design. I have two qubits. H was added on qubit 0, and this is the C naught gate that is added between qubit 0 and qubit 1. So if you understand what this means, people that are going to explain to you will tell you what this means as time goes on. But you can change which one controls by the order of the numbers you put in the QC, in the CX. So if I change it to 1 and 0, I expect this to swap. So they change design. So it's just the way you try to put the number. So which one comes first, which one comes next, which do you use to control what? And then, I mean, you can play with this. This is just to check whether your installation is completely done or correctly done. You can add an extra S gate to the qubit. Then, I mean, you can just do as you like, but one step after the other. So now it's saying that this quantum circuit you see here should create. This is what it means in the Dirac notation. So you have just created a superposition of an entangled state. So entanglement, you are going to learn as time goes on if you have not had it before. So here you have an entangled state. This is the Bell state, and this is just created it in less than maybe 6 lines of code. So with that, now your task. So now this is your task. The first task is generate a 3-qubit GHZ state using Qiskit patterns. Then it's like, what does this mean? So GHZ, as what it means, is also an entangled state, but with 3 qubits this time around. So now you will see, now you can see it's just exactly like this one, 0011, but here you have 000111. So now exercise, design a GHZ gate. So this is how it looks like. Then in this exercise, you will define a GHZ gate following the steps below. So it gives you the hints. Step 1 is to apply Adamant gate to qubit 0, putting it into a superposition. Wow, so sweet. So you already have the gate created for you, the circuit created for you. So I hope I am making sense. Are you still following? Although I'm done, this is just the only one I'm trying to explain. Show of hands. Are you following? Okay, great. Our online participants, are we also following? All right. Okay. So now this is a typical example of how to add to the code. So now it says write your own code below here. So everything you want to write should be in between. Write your own code below here and your code finishes here. So that means this required solution is supposed to be within this section of the code. Okay, I now look at the flow. The quantum circuit has been created. Awesome. Then I need to add a H gate to qubit 0. Oh, how do I do that? I look at the name of the quantum circuit that was created. Don't generate a new name. Just follow what has been done. So I say QC. Now I manipulate it. I add Adamant gate to it on qubit 0. Successfully done. There's nothing extra to do here. Then you move to the next thing. What do I need to do again? Add a C naught gate to qubit 0 and 1. Oh, I understand this. QC, CX, qubit 0 and 1. I put a comma between them. Then I move to the next thing. Add a C naught gate to qubit 1 and 2. Then I do QC dot, now I've made a mistake and I just did QC dot open bracket 1 and 2. This will not work. It will give an error because it's just like an oversight. Then I put CX. Then if I've done everything correctly, my code ends here. Then I should run it. So by running it, I have this. I have an interpretable code by Python, an interpretable code by Qiskit, but then I have a next line which comes with IBM design. So they now want to check this solution that I've provided, is it the required solution? This you are going to have when you have like online participation in IBM challenges. We may not have this kind of structure, and this is why it will be different. So this you have to know whether what you have done is correct or not. So you just have to follow the syntax and understand. But here it is easier. You just run this next line. It checks your previous solution. If it is the required solution, it tells you, yes, your solution is correct. Is this fine? Okay. Then this will not work because you can see grading your answer, please wait, failed, not successful, service unavailable because the challenge is already in the past. So it is not an ongoing or current task. Okay, so I think now with this, I can say that we are done for today. And I believe that we have a nice time learning ahead. So thank you, everyone. So I believe you understood the explanation, everything we went through. You're going to receive these materials, play with them as much as you want. So what you are going to be supplied with will be the earlier material I showed you, empty cells. You have the solution, play with it. Then you also have this lab 0 to work with and practice as the talks are ongoing during your lab session. So during the lab session, ensure that your laptop, you have Qiskit on it, and then you can ask questions as you want, and we'll have some good time together. All right, so thank you, everyone. I'm going to stop here. So question, if there are any, don't ask me how do I install Qiskit on my laptop. Okay, we're going to take that together. Yeah, you have a question. Please go ahead.
Thank you for this insightful vision. So I want to ask, with this on 12 Thursday morning, session, so I want to ask that how do you—
Sorry, I don't know if it is my device here. Your voice seems very low. Let me check.
Like now, we're talking about matrix in the morning. I want to ask, how do you represent our matrix on the quantum computer? Like, is there a way, or is there a way we can represent our matrices on the quantum computer?
Sorry, 1 minute. Let me connect my audio so that I can hear you clearly. Okay, please, you can retake your question again, please.
Okay, sir. I said we need theoretical aspect and the practical aspect. So I wanted to ask that, is there a way we can represent our matrices on a quantum computer?
Is there a way we can
Represent our matrix?
matrix? Yes, of course, of course. Everything we're doing, the quantum security service is a matrix. So you're going to see all of this. You can write matrix directly into your code and also view it. You can see the matrices, of course, using LaTeX. We're going to do all of this. Yes, you can.
Thank you very much, sir.
Yes, because all the gates themselves, they are matrices. We're going to see them.
Yeah, thank you very much for the last session. I think it was quite interesting and encouraging. Throughout the course of the lab session, apart from building circuits, I mean, are there other things we'll be learning?
Apart from
understanding this building of circuits, are there other areas of things we'll be learning? I mean, for the next 3 weeks.
Yes, there will be other areas of things that we'll be learning, but this introductory part is very essential because if you don't get this, it will be much tedious or tasky for us to move.
Thank you.
So any other question?
we've come to the end of this session. And for now, we'll be taking a look for tomorrow, and then tomorrow's session is by 4 p.m. But we are advised to come early so we can start out. So we have 2 talks tomorrow, 4 to 6. We are hoping and expecting that all the year that time. So thanks so much for today. A round of applause for Mr. A round of applause for everybody. Okay, thank you very much. Let's come up. Thank you. Let's come up. Yeah.